Hello everyone. In this video, I'm going to help you to solve the problems 1 to 4 in the section 5-6. Let's start with the first problem. The first problem involves the use of stereonets and converting a quadrant notation to an azimuth notation for strike and dip. In this example, I'm going to solve just the first problem, and then you'll solve the other three. So let's see what we do first. I already created my stereonet here on the right, and I'm going to go ahead and find what are the poles of all those faults. Let's start with the first one, and here I know that the strike is 55 degrees from the north towards the east, so that means that there is going to be a strike line that is going to go 0, 45, 55 degrees somewhere over here to somewhere over there. The strike line, remember, is the intersection of the horizontal plane and the plane of the fault. The second thing that is going to happen here is that we need to identify what is the dip. The dip in this case is 45 degrees towards the southeast. That means it's going deeper in the direction of the southeast. If the fault that we cannot see in this 2D projection, but I ask you to imagine that if this is the strike and it's getting deeper in this direction, then a line perpendicular to such plane is going to go into the opposite direction. So if the fault is deepening and getting deeper in this direction, then the pole is going to be opposite to that. And in order to do that, I'm going to trace a line which is perpendicular to this line. And this is going to be a line that goes more or less like this. And depending on what is the dip of that fault is where this pole is going to be located along this line. For 45 degrees, as I have it over here, the dip is going to be in between 30 and 60. So the pole is going to be a point right there. This is the pole of the fault. The strike angle then is 55 degrees, and the dip is 45 degrees. Let's see how you can check this result with your stereonets. So if you click on this link, you will be directed to this web page in which I have already created the same plane, and this one is going to allow us to see in 3 dimensions. This is the plane of the fault. Is dipping towards the southeast. The pole is a line perpendicular to that. It's hitting the lower hemisphere projection at this point. And when we look from the top, what we see is the pole in that direction. You can check your numbers here. You see the first number is a strike. The second number is dip. And this is your fault. Just one thing I'm going to tell you to be careful. This stereonet, it's applying the rule in which your strike is related to your dip as well. In this particular problem, the first element of a right-handed coordinate system is going to be the dip. That's going to be your index finger. Imagine that you point your index finger down in this direction. If you do that, when you try to point your second finger or your middle finger, that's going to be in this direction. And the angle between the north and the strike is going to be 55 degrees. If I had a conjugate fault going in the other direction, you will have to use this angle, and for that such fault, the strike will be 55 plus 180 degrees. So I don't want to get into many details about this. I told you that whatever strike you give me, either this one or that one, that will be fine for this class. Okay, let's go to problem number 2. In problem number 2, you're asked to find what the ideal orientation of a hydraulic fracture and shear fractures or faults are for given stress conditions. So let me tell you what the workflow for solving that problem would be. You already have 2 examples of these in the notes, so I'm not going to go in detail about how to solve this problem. You can check it there later on. But in problem number 2, the first thing I would do would be to identify what your stress regime is. In this case, you can see that the highest stress is horizontal and the minimum stress is vertical. And for this particular case, then we see that this is a reverse faulting stress regime. The second thing I would do is to identify what is the direction of the horizontal stress. And I can summarize that by saying what is the azimuth. The azimuth is equivalent to saying what is the direction or the angle between the north and such line. The azimuth of either SH mean or SH max. Remember that SH mean is going to be always perpendicular to SH max. So if you know the direction of one, you're going to know what is the direction of the other. And in this particular case, we see that the maximum horizontal stress is striking east-west. So SH max is striking at direction east-west. Okay, with this data, we can already find what is the orientation of a hydraulic fracture. So the first thing I'm going to do is to draw a block diagram that is going to identify these conditions. I see that one of the horizontal stresses is aligned with the east-west direction, and therefore that's going to make it easy to do a 3D drawing. So I'm going to go with a 3D drawing of this. If I had any of these horizontal stress not to be aligned with east-west or north-south, it will be a little bit more difficult to do a 3D drawing, and you will do a top view drawing, but in this case we're going to do a 3D. I'm going to start drawing such block that is representative of this particular situation. And in this particular case, this should be valid, given that this is the north, this is the east, and this is the depth axis. What this tells me is that, let me tell you why I drew it this way. I drew it this way because I'm drawing the shape of this prism so that the longest side is aligned with the value of, or with the direction of the maximum principal stress, which in this case is horizontal, is going east-west. So that's why I made it longer in direction east-west. My stresses are going to be maximum principal stress, S1, SH max, intermediate principal stress perpendicular to this one, S2, SH mean, and the least principal stress, S3, is the vertical stress. All right, with this information, I'm already able to say what is going to be the ideal orientation of a hydraulic fracture. Remember that a hydraulic fracture is going to be ideally always a plane that opens up perpendicular to the minimum principal stress. And if the minimum principal stress in this case is vertical, that means that a hydraulic fracture plane is going to be a horizontal plane. Let me draw that plane here. Let's say that I fracture this block right in the middle. The direction of that hydraulic fracture would be a horizontal plane. This would be what you would expect as a hydraulic fracture. What is the strike of that horizontal plane? Well, we cannot tell because it's a horizontal plane, right? So this is just a horizontal plane, and the dip will be equal to 0. You could write that, but it doesn't have any strike because you cannot define that. Let me add that here. The dip is 0 degrees. That would be the ideal shape. All right, this is the first part, part A, the hydraulic fracture. This is the easiest part, but also is very important. Remember, a hydraulic fracture ideally will be always a plane that opens up perpendicular to the minimum principal stress because that's a configuration of least energy or least work in order to open up. The second step is a little bit more difficult. Now we have to identify the shear fractures. In order to identify the shear fractures, we need to use the friction angle. And the friction angle is going to depend also in the friction coefficient. So in this case, the friction coefficient is going to be the arctangent of the friction coefficient. Let me tell that again. I don't know if I say it correctly at first. The friction angle is going to be the arctangent of the friction coefficient. So in this case, for 0.5, that's going to be, let's do it quickly here, arctangent of 0.5 is going to be equal to this amount of radians, and let me multiply those radians to convert it to degrees. This is going to be that times 180 divided 3, 4, 15, and you could put a few more numbers, but it's going to be 26 degrees. So the friction angle is 26.6 degrees. We want to know this friction angle because the ideal orientation of the shear fractures is going to depend on that friction angle, and those are going to be located at the characteristic angle of 45 degrees plus the friction angle divided by 2. And in this case, this is going to be 45 degrees plus 13.3, which is going to be, if my math doesn't fail, 58.6 degrees, 3 degrees. Okay, so now that we have that characteristic angle, we're going to call it beta in this case. I'm going to use this rule that we have used before. And let me find it over here. Ideal orientation of faults. This is what we have to use. We know that these ideal shear fractures or faults are going to be oriented in two possible orientations, and they are going to be going at an angle of beta from the plane of the maximum principal stress to the plane of the minimum principal stress. So look at this in this plot, and uh, you can see which one is S1 and which one is S3. The only information that we're missing now is with the betas, well, that we already calculated in here, but we're going to have to put these planes over here. So let's go ahead and do that. I wanted to do those two with green. The angle is 58.3 degrees from the plane of the maximum principal stress towards the plane of the minimum principal stress, which is this one, and the result of that is going to be a fault that is going to be more or less like this. This is one of the possible solutions, and here this angle over here is 58.3 degrees. The other possible solution is going to go in the other direction. I'm going to draw it here, but I'm not going to give you the entire solution, okay? But let's say that it starts somewhere over here and it goes all the way up there, and this is the intersection with the horizontal line. The same angle beta applies there. But for this fault number 1, I can see from the figure what is the strike. The strike is this line, the intersection of the fault with the horizontal plane, and in this case is equal to 0 because it's in the direction of the north. It's aligned with the north. And the dip, notice that it's not given by the angle beta, but by the complementary angle, which is right here. And this angle over here is going to be 90 degrees minus 58.3 degrees. You can do the math, you can get the solution, and for fault number 2 is going to be pretty similar. Now that I do fault number 2, I see that I'm missing something over here. This dip, you can see fault number 1 is dipping towards the east, so we're going to add an E over there. Fault 2 is going to be different. Problem number 3 is quite similar, but with another state of stress. So it's not going to be exactly the same, but it's very similar, and you have some examples in the notes. I also explain how to do one of those. First, remember, recognize the stress regime, the direction of one of the horizontal stresses. With that, you can already tell what the hydraulic fracture orientation is, and then later you can get the orientation of the faults or ideal shear fractures. And the fourth problem is the inverse problem to problem number 1. In this one, I'm giving you the poles of a number of fractures, and you have to say what is the stress regime and the direction of the stress that cause such faults. For example, here you see that we have faults which have a dip of 30 degrees, and the strike, remember, is going to be given by a line perpendicular to the line that joins the pole with the center. So if I take this point here in the middle, let me zoom in. I take this point right here, perpendicular line is going to be this line, so such strike is going to go north-south. Faults that have a more or less low dip is going to be something very similar to this. And that's going to mean if they have a low dip, less than 45 degrees, that they are likely caused by horizontal stresses being the maximum stress direction. Why? Because always these shear fractures form such that the angle between the plane of maximum stress and the plane of minimum stress is larger than 45 degrees. And we know that equation very well. So this always is going to be an angle higher than 45. And therefore, this is going to be less than 45. If this one have a low dip, then that means that this is very likely a stress regime fault. And it appears that actually this is very similar to what we have in this example, where the maximum horizontal stress is oriented east-west. That's why the strike is going north-south. You have two more examples to solve over here. I'm going to give you a hint. One is normal faulting, and the other one is a strike slip. You have to find out which one is which. But if you go to my notes, you probably will recognize those. And let me show the, the, the diagram that you need in order to solve that. The basic drawing that you need is this. And then you need to apply this to the three different stress regimes, either normal, strike slip, or reverse. And that's going to give you the solution about in which stress regime you are. Notice that in all these examples in this figure, I have assumed that the minimum principal stress goes in east-west direction. And that's the result for what you see over here. But if the horizontal stress, in this case the minimum stress, is not in east-west direction, but is in any other direction, the location of these poles is going to change. So that's what you have to notice, and that's what you have to tell me in this particular example. So we say that for problem number A, the maximum horizontal stress is east-west, minimum principal stress is therefore north-south. You have to tell me the orientation of those two for B and C, and also what the stress regime